Today, we are going to dive into one of the most fundamental ideas in all of physics. It's a concept that connects the sound of a passing car all the way to the very edges of our expanding universe. This is the relativistic Doppler effect explained.
So let me ask you this. What could a speeding ambulance, your local weather forecast, and the entire universe possibly have in common? I know, it sounds like the beginning of a really weird joke, right? Well, the answer comes down to a single, really powerful idea. It's all about perception and how the simple act of moving changes the very waves, whether it's sound or light, that are reaching you.
To really get this, let's start with a sound that I guarantee you've heard 1,000 times. The secret to this whole thing is actually hidden right inside the wail of a passing siren.
Okay, so this is what's known as the classical Doppler effect. A guy named Christian Doppler figured this out way back in 1842. And it's all about this idea of a shift in frequency. See, as a source of waves moves towards you, the waves get all bunched up, compressed. And as it moves away, they get stretched out.
And here's the part you've actually experienced. For that ambulance siren, those compressed waves hit your ear more often, which your brain hears as a higher pitch. That's that nee part of the sound. Then, as it passes you and starts moving away, those waves stretch out, hitting your ear less often, and the pitch drops. That's the Pretty simple, right?
For sound, this is all pretty straightforward. But, and this is a big but, when we try to apply that same exact logic to light, physics just hits a wall, a huge roadblock. Because, as it turns out, light doesn't play by the same rules.
Just think about it for a second. Sound waves have to travel through something, a medium, like air or water. That siren's sound is just vibrations in the air. But light can travel through the total, complete emptiness of space. So what is it moving relative to?
And that is the huge problem here. The classical theory, the one that works so well for sound, absolutely depends on having that medium. Without it, the whole framework just kind of falls apart. For light, there's only the source, like a star, and the observer, us. There's nothing in between.
And this whole problem leads to a really weird inconsistency. The old classical equations actually give you two different answers for what should be the exact same physical situation. I mean, a car driving towards you at 60 miles an hour should be physically identical to you driving towards a stationary car at 60 miles an hour, right? But the old math said, nope, they're different.
And this was the question that had physicists just scratching their heads for decades. For light, it just feels so intuitive that only the relative motion between, say, a distant star and our telescope should be what matters. The old formulas just weren't cutting it.
And this is where our story takes a really dramatic turn. Because we need to talk about a young patent clerk working in 1905 who was about to change literally everything. We need to talk about Albert Einstein.
You know, this idea had been building for a long time. Doppler nails it for sound, then Fizeau tries his best to make it work for light, but it was Einstein's theory of special relativity in 1905 that finally gave us the key. And get this, it wasn't even until 1938 that experiments by two guys, Ives and Stilwell, came along and definitively proved he was right all along. So if you look at the old formula and the new relativistic one, you might think, what's the big deal? They look almost exactly the same, especially when things aren't moving that fast. The difference seems so tiny, just a little tweak in the math. But that one tiny change, well, it accounts for the strange reality of our universe.
Okay, so here it is, this secret sauce. It's this tiny term right here. This is Einstein's special ingredient, what we call the relativity term. And what it accounts for is one of the most mind-bending ideas in all of physics: time dilation. The faster something moves, the slower time itself literally ticks for it. By factoring in this slowing of time, Einstein's formula works perfectly. It doesn't matter if the source is moving or the observer is moving. Reality is symmetrical again.
And if you think that's weird, hold on. This whole time dilation thing leads to an even stranger prediction. Einstein's math showed that because a moving clock runs slow, you should actually see a frequency shift even if a light source is just moving sideways across your field of vision, not getting closer, not getting farther away. The old physics said, no way, that's impossible. But incredibly, experiments proved relativity right again.
Okay, so this isn't just some abstract, dusty old theory. The Doppler effect is a fundamental tool that we use every single day, and it shapes everything from our weather forecasts to our most basic understanding of the cosmos itself.
For example, this is a life-saving application we rely on constantly. Weather radar works by bouncing microwaves off of raindrops. By measuring that tiny frequency shift, Meteorologists can see not just where the rain is, but how fast it's moving and in what direction. It's how we get those crucial warnings about severe storms.
Now let's zoom way, way in, to a much smaller scale. Doctors use the exact same principle. Doppler ultrasound sends sound waves into your body and measures the frequency shift as those waves bounce off your moving red blood cells. This lets them literally see how blood is flowing, helping to diagnose all kinds of issues, all without a single cut.
And of course, there's the one application that some of us might have a more, personal experience with. A police radar gun is a Doppler device, plain and simple. It bounces radio waves off your car and measures the frequency shift to calculate your speed with incredible accuracy.
All right, let's scale this whole idea up to the entire cosmos. For light, we have special names for this effect. When a light source is moving towards us, the light waves get compressed. This increases their frequency, shifting them toward the blue end of the spectrum. We call that blue shift. And when a source moves away from us, the waves get stretched out. This decreases their frequency, shifting them toward the red end of the spectrum. And that is red shift.
So back in 1929, an astronomer named Edwin Hubble pointed his telescope up at the heavens and noticed something that would change everything. No matter where he looked in the sky, the light coming from distant galaxies was almost universally redshifted. They weren't blue, they were red.
And the implication of that observation was just staggering. It could only mean one thing. If pretty much everything is redshifted, then pretty much everything is moving away from us in every single direction. The only possible explanation was that the entire fabric of space itself is expanding. And that leaves us with one final, absolutely mind-bending thought. The Doppler effect lets us see the universe expanding right now, today. So if we could run that cosmic movie in reverse, tracing that redshift all the way back in time, what does that tell us about the very moment it all began?